Andrews, and I am currently the Maths Coordinator at Highfield South Farnham, and I'll be taking you through this SOS session on geometry, focusing on shape, position and direction. So first of all, let's look at the aims of the session. So hopefully by the end of this session, you will have an understanding of mathematics in the national curriculum and its development throughout from Key Stage 1 throughout into Key Stage 2, and to enhance your subject knowledge of the pedagogical approaches to teaching maths. So if there are any areas that you're not sure about in terms of geometry, hopefully you will have some inspiration from this session. And also to develop an understanding of what a child needs to demonstrate mastery of mathematics, of a mastery of a mathematical concept. So we'll have a little delve into some mastery questions and some SATs questions at the end. So we're really clear about where we're aiming for at the end of Key Stage 2. So broadly, the areas of curriculum that children need to cover are radius, diameter and circumference, so the parts of a circle, which they tend to kind of learn more towards the end of Key Stage 2. Angles, which largely builds on their learning of turns, like half turns, quarter turns, which they learn in sort of Key Stage 1. Then they move on to, they also look at describing position on 4-quadrant grids, and looking at symmetry, rotation, position and translation. 4-quadrant grid tends to kind of come up towards the end of Key Stage 2. They tend to start with just 1 quadrant to begin with, and also to compare and classify geometric shapes. Also looking at area of parallelograms and triangles, as well as the rectangle. And also they will be looking at volume, but just really cubes and cuboids around sort of Year 6. Okay, so that's sort of the areas covered in a nutshell. So in relation to your year group, this is sort of the progression in relation to properties of shape. So if you're teaching Year 3, it might be helpful to look at Year 2 and Year 4 as well, just to get a sense of where they're moving towards. And here is a brief look, breakdown of Year 5 and Year 6, and see sort of the transition into drawing angles. There's a greater focus on angles sort of later on, and in Year 6 looking into different types of triangles and quadrilaterals, and then finding missing angles, looking at different rules in relation to geometric shapes and applying them. So as well as shape, there's position and direction. So those are the two sort of broad areas that children cover. So in relation to position and direction, here's the progression. Year 3 doesn't tend to cover much on position and direction. It is merely sort of consolidating what they've covered in Key Stage 1, and also there's a lot to cover in Year 3 in terms of shape. And then Year 4 and Year 5 and Year 6, we tend to look more closely at those transformations. Okay, so just to get us thinking about where it all starts, I'd like you to look at the photographs and think about, are these children experiencing mathematics? So look at them in action. What kind of maths do you think that they are experiencing, if any? Okay. So I'll just give you a moment to think about that. So as you look at it, you might pick out that those children who've found those trikes at the bottom and then coming around that pathway, they're playing at high speeds around various obstacles lying around in the playground. They might have to judge the gaps that are large enough, whether they're large enough for them to squeeze through, also sort of navigating their way around boundaries to the left, to the right, looking at different positions and directions. Also, that boy experiencing that curve of that bridge as opposed to it being very flat in the run up to it and after it. And also children understanding the boundaries and relating their route to the position of other children following them. You see, they're always very clear about who's in front and who's behind them. Okay, so lots and lots of different experiences there that really sow the seeds for their understanding of those later concepts. So in geometry, there are two basic concepts that children just need to understand in relation to shape and space. And so number one is to classify, so understand what's the same about shapes. So for example, if you had a green square and an identical yellow square, asking them what's the same and what's different, so the colour would be different, but they still have four sides, they still have four corners, they still have those properties that are familiar. So really getting children to identify what's the same helps them understand, and also identifying what's different. Okay, so those are the two sort of key areas, and I'll explain those a little bit more as we go further on. So here's a nice activity to play with your children if you want them to sort of start generalizing about what's the same and what's different. So here's one in relation to numbers. Have a little look and see if you can identify what my rule is. Okay, you guessed it. So the one that says yes on the left-hand side, the rule is numbers less than 11. Okay, so those numbers on the left-hand side are less than 11. So that yes, they follow the rule, and no, the ones on the right do not follow the rule. And you can apply this to multiples and factors and all sorts of other different numerical ideas. Also, this fits in really well with shape. Really nice one to play as well. So here is another example. Can you identify what rule is at play here? Have you guessed it? So the one on the left, they are all have at least one pair of parallel sides. We talk about parallel as being two lines that are always the same distance apart. They never grow closer, they never go apart. They are like train tracks. Okay, so you've got two pairs of parallel sides on the square as well as the rectangle, and then you've got one pair of parallel lines on this trapezium at the bottom of that left hand side. So children experience a 3D world of solid shapes, but it is important that 2D experience and 3D experience go hand in hand. So a child can become confused between an oblong and a cuboid, which is why the oblong should be referred to in relation to its surface. One teacher that I saw who did particularly well in supporting this understanding held the shape of a cuboid in a cloth for them to only identify the face, okay, which happened to be a square, so the end of the cuboid, and she pushed it out to reveal that it was a 3D shape. It's a nice way to kind of help them understand the association between 2D and 3D. Also another activity to help them, as you can see in the pictures, there's some printing going on, getting them to kind of understand the properties of those 3D shapes. So even though you might not mention it's the face of a shape or the edge, just merely the experience of printing helps them understand that as a feature of that shape. So let's have a look at some of the transformations. So let's have a look at these shapes. Let's look at translation. So look at them carefully. What is the same and what's different? So they're all rectangles with a diagonal line from the bottom left to the top right hand corner. They have the same dimensions. The angles are the same. Two pairs of parallel lines. They differ in position. This is a fundamental concept in the study of space and shape. It is really important to ensure that your children experience their vocabulary. Here, there, nearer, further, closer, higher, lower, above, below, in front of, behind. To describe translation, we need up, down, left, right, forwards, backwards. So really nice opportunity to do some sort of blindfold games, or using chalk in the playground, making a giant coordinate grid and making it a human coordinate grid. So getting children to actually physically move on that grid to show the translation of a shape. If we tell children to sit at the same table as yesterday, we would expect them to take the position into account. The table might be the same shape and same size, but when we say the same table, we mean the same position as well. So it's really important to think about what the vocabulary that the children are used to and try and think about some of their misconceptions. So, as well as translation, as a transformation, there is rotation. So have a think about these. Are they the same? How are they different? And what do you think children need to understand in order to access rotation? Okay, so rotation is different to translation. It's the same shape, just like translation, but it's a different orientation. So to go from one shape to another, the transformation is rotation. In order to access this, children need to understand angles. So for example, a quarter turn, or to turn the shape a right angle, or to turn the shape a half turn. This would come up in year 2. So manipulating shapes and doing your quarter turn, your half turn. What children find quite useful is actually having a hands-on shape just to practice that orientation. Also, it can be related to the clock face as well. So talking about clockwise and anti-clockwise at year 2 as well. Now, lots and lots of vocabulary is associated with geometry, and a lot of the curriculum is centered around calculation now. So how can we ensure that children really retain the vocabulary that they need to kind of access throughout Key Stage 1 and Key Stage 2 in relation to shape and position and direction? So here are some ideas about how you can bring vocabulary into the children's learning environment. So around your door or around your clock, reinforcing the understanding of quarter turns and half turns, and also higher up, the understanding of perpendicular. Children have a pre-existing understanding of that as a right angle, and then you introduce it as perpendicular. So it's really helpful if they can see it in real life so they can access it as a concept. And then at that point, they're able to apply that knowledge later on with more unfamiliar questions. Another area of transformation that the children might look at is rotational symmetry. And this is a bit later on in Key Stage 2. Sometimes a shape does not change when it is rotated through certain angles. This shape could be rotated a half turn and it would look exactly the same. So therefore it does have rotational symmetry. Okay, So let's have an experiment. There are some letters below. Which letters have a rotational symmetry? Okay, have you guessed it? So S should have some rotational symmetry, whereas A will not. Neither will C, but N will have rotational symmetry as well. So again, getting the child to physically turn shapes around to identify rotational symmetry is a really good starting point. And then on to reflection. So the transformations, rotation and translation, are regarded as the same shape. So going back to those two concepts, what's the same, what's different, we're always relating back to that. Reflection is a change. Okay, so it's sort of distinctive from the other forms of transformation. So here we have our mirror line, that's the language. And then you've got your original shape and the reflection. So usually children might do this sort of later on squared paper, so they can kind of count squares, especially away from the mirror line, which will help them a little bit. Children tend to find it much easier to find a reflection in their shape when it touches the mirror line. When shapes move about, they've got to think about the reflection itself as well as considering the distance. So using mirrors and tracing paper in the early stages of learning reflection is a really good way to boost children's confidence in the area. Okay, another vocabulary that you might come across is the word congruent. So if we disregard the transformations, so translations, reflections, and rotations when comparing these shapes, we would say they are the same. We call them congruent. Okay. Now there are lots and lots of different vocabulary that we'll come across. One really useful resource is a glossary which can be downloaded from the NCTEM website. I will show you what that looks like at the end and give you the address. But it's really good to print that out, spiral bound it, and just have it as your Bible to refer to, because it just has a glossary of every single mathematical vocabulary you will need to come across from Key Stage 1 all the way through to Key Stage 3. So there's lots there to help you out if you come across anything that you're not quite sure about before you teach. Okay, also scaling. So we think about scaling in the context of multiplication, but we also need to think about scaling in relation to shapes. Okay, so making that generalization. While some shapes are the same, they can still change in size. Okay, so this is another change, just like reflection was. A child might experience this idea when sorting sets of triangles, while still regarding them as the same. Okay, so even though the square is bigger, it is still a square. Even though the green square is now yellow, it is still a square. So it's really important in terms of refining your understanding of those properties by just having these experiences, outlining what's the same and what's different. Okay, so here is a typical SATS question, so in Year 6, and I've got a diagram here of a positive scale factor. So the shape is enlarging by a number of times, and we say there's a scale factor. And also, if you have a scale factor less than 1, it's getting much smaller, so it's half. So this triangle on the side, if it's a scale factor of a half, it's obviously half the size. Now it's easy to work that out on squared paper like this question here. So enlarge shape K by a scale factor of 3. Draw your answer on the grid. So another activity to do, have a look at the child's answer. Initially it might look correct, but it's not quite. What misconception do you think this child has, and how might you address it? Okay, so maybe you can see here we've got one side. Okay, it's that vertical line there of 2 squares. Scale factor of 3 should be 6. 1, 2, 3, 4, 5. They've done 5 squares. So they haven't got that sort of they haven't associated with that multiplicative element, which emphasizes the experience of scaling through number as well as shape. It's really important from EYFS through to year 6. Also, scaling brings in the inverse relationship. So a negative scale factor means to divide. So so for example, if we had or if we wanted to do a scale factor of a half, that would be divide by 2. So associating, the children need to have understood that understanding of like multiplying by a half is the same as divide by 2, multiplying by a quarter is the same as divide by 4. Okay, another area that children will look at is quadrilaterals. So reflect on your learning so far about equivalence and transformation. A nice activity, a nice resource to use for an activity like this would be pegboards. So create 3 shapes. You get one of your children to create 3 shapes, maybe 3 of the ones they know from the list, and ask them that meet a certain criteria. So can you create 3 shapes that have all equal size? Can you create 3 shapes that have 1 pair of parallel lines? Pegboards are a great way to really get the children thinking about those properties. So look at the shapes here on the screen and the properties. Can you match them up? So for example, all sides equal. The shapes that would correspond to that property would be a square and a rhombus. Have a look at some of the other properties. Can you identify what the other shapes would be? And here is another thing. So true or false? A square is a type of rectangle. A rectangle is a type of parallelogram. A square is a rectangle, therefore a parallelogram is a rectangle too. All rectangles, including squares, are parallelograms. And rhombi and parallelograms with sides of equal length. Okay. So which one do you think is true? Which one do you think is false? So it turns out that they are all, in fact, true, which is mind-blowing. So, but an easier way to think of this is visual. So I've got a visual here that just sort of breaks it down and makes it a bit easier. So if we've got a square at the bottom, which is a special type of rectangle. And why do you think it is a special type of rectangle? Because it has 2 pairs of parallel sides. A square is a special type of rhombus. Why is it a special type of rhombus? Or why is a rhombus a special type of square? Because it has 4 equal sides. A parallelogram is a special type of rectangle. And why is that? try and think about what are the properties that are the same, what they have in common. And all of those shapes are all types of quadrilaterals. So what do they all have in common? What is the same? Another area is triangles. So here's a nice diagram that just kind of breaks everything down into categories. So we have a scalene triangle. So a scalene triangle is a triangle with sides, with no sides that are the same. And to demonstrate that, the bottom triangle has got those red lines to demonstrate that those are not the same length. The isosceles triangle, as it has those two lines marked, so one line on one side and one line on another side, demonstrate that those sides are identical length. And the same is with the second and with the third. I just have marked it in there. But two angles are the same and two sides are the same in an isosceles triangle. And in an equilateral triangle, it's in the name, all the sides are equal in length and all the angles are equal in length. And here we are with some sort of true or false questions that you could perhaps pose to your class. Which one can have an acute angle, which one could have a right angle, and which one could be obtuse. I've popped it here in a sort of a Carroll diagram, just for it to just demonstrate it. Here is another fun activity for children to discuss some of the rules associated with triangles. So in a triangle, all the interior angles add up to 180. So you could get your children to create as many different triangles as they want. So it could be, or different types, not too many, but they could make, the point is they could make an isosceles, they could make an equilateral, a scalene, a right angle triangle, all the different types. But no matter what type it is, if they were to cut off the corners, as I've demonstrated in the picture at the bottom of that PowerPoint, and then to the left of that, sorry, to the right of that, I've assembled the noses of those angles together, which then form a straight line. And we know the straight line, angles in a straight line, add up to 180, which that proves the theory that all the angles in a triangle add up to 180. So what is the angle of every single equilateral triangle? Well, it would have to be 60, because you put 3 of those angles that you know to be equal, and 180 divided by 3 is 60. So every equilateral triangle would have 60-degree angles. Okay, so that's a really nice activity to try. Also, and I haven't popped it on here, a very similar concept, the children will need to understand that all angles in a quadrilateral add up to 360. So they could cut out a number of quadrilaterals that I've identified in this diagram. So parallelograms, trapezoids, rhombi, squares, rectangles. And then if they cut off the corners and assemble those similarly to the triangle, all those corners should make a 360 turn. Okay, so they should all meet together and complete a whole turn, thus proving that all the angles in a quadrilateral add up to 360. It's a really nice investigation that helps the children in a hands-on way remember that rule rather than rote learning it. They're more likely to retain. Okay, so angles that children will need to learn. So here on the left-hand side, we've got an acute angle. You think of it as acute, tiny. It has to be less than 90 degrees. Right angle, which they will come across in year 2, so quite early on, is 90 degrees. Obtuse is greater than 90, but less than 180. you've got a straight angle there of 180, and a reflex angle which is more or greater than 180. The angles that they will need and rules they will need associated with those angles are as follows. So they'll need to know, obviously, that right angle is 90. They'll also need to learn that opposite angles are equal. Some of the measures of angles on a straight line add up to 180. And the sum of the measures of an angle around a single point add up to 360. So those are all the rules they'll need to come across in a nutshell when they need to identify missing angles, which, if you refer to earlier when we talked about the progression, this is likely to come up more in year 5 and year 6. Okay, so measuring angles and drawing angles. So later on in Key Stage 2, children will be introduced to a protractor. Now, to measure and draw angles. So let's think about some of the misconceptions that children might experience when using a protractor. So if a child said that angle is 3 degrees, what misconception do you think they might have? So really need to be careful to think about maintaining the idea that an angle is still a turn and it starts from 0. So as almost like scissors, as that angle opens up, you need to follow from 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 120, and it looks like 127 degrees. So following the line from 0 degrees, like a pair of scissors, how the angle kind of opens up. Also, to challenge that misconception, you can refer back to their knowledge of acute and obtuse. If you were asked to draw an angle of 52, that would have to be an acute angle. And what have you drawn? You've drawn an obtuse angle. So getting them to refer back to acute and obtuse. Can it be true? Also, another area they find quite difficult is positioning the protractor. So the right in the middle, sitting on that line, understanding that sort of accuracy, where the nose of that angle needs to sit right in the middle point of the protractor to ensure as accurate as possible. However, most questions in any of the tests they have will give them a margin of error of 1 or 2 degrees. So it's really important that they understand how to use these protractors early on and get lots of practice. So those are the main whistle-stop tour of all the areas that they will need to cover in relation to those 2D shapes and transformations. So here was an example of a SATS question. Circle the pentagon with exactly 4 acute angles. So they're applying their knowledge of 2D shapes and their knowledge of angles here. Okay, have you spotted it? Okay, so it's the shape second down on the left hand side. Looks like a sort of an M shape, the one that has those 4 acute angles. Really nice question there. So the challenges are understanding of a pentagon, what's the same, what's different. So it still has 5 sides, therefore it is a pentagon. But it's concave, like some of the sides come into the shape. Okay, so there has been a change, but what remains the same as those 5 sides, that is still a pentagon. So quite a nice activity there. And missing angles. So here is an activity, a Year 5 extension activity. Can you identify the missing angles using known facts? Angles on a straight line using 180 degrees, and angles that form a right angle, total 90 degrees. So A is quite a nice subtraction one. 90 by 63. Okay, and then you can find out D, because you know A by that point. There's a right angle at the top, so you can subtract that from 180 to find out D. So a nice sort of problem solving activity there, finding out your missing angles. Just have a pause and see if you can answer some of those using the rules that we've talked about. And here is another question, another style question. So calculate the size of angles A and B in this diagram. So think about what the children need to know. So those two rules, main ones, vertically opposite and angles in a quadrilateral, will enable them to access question A and question B. So another one to have a go and see if you can solve using what we've discussed. Okay, right, another area that children will need to learn in relation to shape is 3D shapes and polyhedrons. Similar to polygons, those sort of regular 2D sided shapes, a polyhedron consists of faces that are the same shape. So here we've got some vocabulary associated with that cube there on the corner. So the face is flat. You've got a vertex. So all those edges meet up to that vertex. And then you've got that edge there where two faces meet. Okay, so just a quick sort of test to make sure that we understand those. So how many faces does a tetrahedron have? Cube, octahedron, a dodecahedron, and an icosahedron. Can you think about what the faces would be as well as the vertices, edges? Also, another area that the children will need to look at is nets. So a really nice way to kind of introduce them to 3D shapes is getting them to just look around the room, going on a bit of a shape hunt, being able to identify 3D shapes in their normal setting, finding maybe old cereal packets or kind of kitchen things that they can kind of break down into the original net, so they can see, sort of work it backwards, what are the number of faces that they need and how are they connected in order to make a successful 3D shape from a net. So lots of really hands-on material would help with that. So at the end of this, I have got a slide outlining a really good website where I can have a closer look at faces, edges, and vertices of lots of different 3D shapes. So I'll explain a bit more about that at the end. Prisms. So coming back to that activity that I talked about earlier in EYFS, where that teacher had a 3D shape and she'd kind of just exposed its face and hidden the rest of it in a cloth and then pushed the face out. That's quite a nice activity to kind of revisit when you are teaching the concept of a prism. Okay, it's kind of a face that's sort of been stretched out, and if you cut into slices, each slice would be no bigger or smaller than the one before. So think Toblerone, think of cheese, think of bread. So some real life examples of prisms when you start to kind of associate them with, and then it's a lot easier to identify them. We've got an example here of a hexagonal prism, pentagonal prism. So it's just really kind of using that knowledge of those polygons to help you really. And pyramids. So a pyramid is made up of a polygon forming the base. So we've got square base, circular base, hexagonal base, triangular base, diagonal base. And the lines drawn up from each of the vertices of this polygon to some point above. Okay. And then we've got our real life example of the pyramids there. Okay. So you can form some nice generalizations in those shapes. What's the same, what's different. Okay, let's have a bit of practice using what we've looked at. So here's a typical SATS question. Tick each shape that has the same number of faces as vertices. So a application of properties question, and I would say the answer is square-based pyramid and triangular-based pyramid. Square-based pyramid has 5 faces and 5 vertices, and a triangular-based pyramid has 4 vertices and 4 faces. Another area is perimeter and area. So area is the measure of 2-dimensional space within a boundary. The perimeter of a shape is the length around its boundary. So whenever you're introducing these topics, it's a really nice way to kind of relate it to a real life text, because the two tend to get muddled up sometimes. So if I'm introducing area with the children, I might think of like tiles on a kitchen floor, or if you're thinking about perimeter, I usually refer to when they've done their warm-ups for PE and they've had to go around the perimeter of the AstroTurf. Or I might give them an example of it being Christmas. I wanted to put some tinsel around the whiteboard. How am I going to know how much tinsel I need when I to pick it up? So getting them to really break down and think about what it is to find the perimeter and what it is to find the area. Okay, and then when it comes to the formula, it kind of makes a bit more sense. For area, they'll tend off, as it looks in the example, as counting squares as arrays. So understanding that. So early in key stage 2, they would associate areas as an array of squares. And then later on, to be more efficient, rather than counting, they can think about just multiplying the numbers out. Okay. With triangles, it's quite easy if you cut out a square and cut it in half, you could quite easily demonstrate why the area of a triangle is half the base times height. And the same with parallelogram. Like popped in that drawing there, you could cut out a parallelogram and cut off that triangle at the end where it slants down, and then refit it on the other side to form a rectangle, thus proving that it's still length times the width, like a rectangle. Okay, these are quite old moments for children. It's really important that they get to handle the shapes, get to cut out, get to kind of get a feel for why these formulas work. Will really sort of bolster their understanding. Okay, so as I mentioned earlier, right at the beginning, they will need to be able to identify the parts of a circle. So I stand up in front of the class, get the children to stand up. My body is the centre of the circle. I put one arm to make the radius, put out both arms in a straight line to form the diameter, and then one arm out. I turn round 360 degrees to demonstrate the circumference. So I usually start off with children actually saying this vocabulary with the physical actions. Very Bruno, really helps them kind of understand it, and a little bit silly, but it's those sort of things that help them retain that understanding. So if they understood radius, diameter, and circumference, then they might be able to tackle questions like this. So here's an example of a SATS question. So you've got 4 large circles, 5 small circles fit exactly inside this rectangle. The diameter of the large circle is 17.5 centimetres. Calculate the diameter of a small circle. Right, and I'll leave you to have a moment to get on to see if you can solve that one. Okay, so the way I would tackle this question is I would add up. I know that there are 4 parts in the whole length of that rectangle. One of the parts is 17.5. So I would multiply that out by 4. So I'd get the full length of that rectangle, which would bring me to now 17.5 or 17.5 plus 17.5 is 35. I double it and double it again to make the 4, so that's 70 centimetres. And then the length, I know that those 5 small circles, the combined diameter of those must be 70 because it's the same. So then I'm doing 70 divided by 5 to find out that diameter of that original circle, which should be with 14 centimetres. Here's another trickier one, mastery, year 6. So here's a tiled floor plan. It's made from equilateral triangles, squares, and a regular hexagon. Work out the perimeter of the design and give your answer in meters. So have a look. So the 2-part answer to this question. Okay, have you figured it out yet? It's quite a tricky one. So the way I think there's lots of strategies that people could use to try and solve this one. The way I tackled it was I thought of that hexagon being a combination of, because those squares and those triangles have the same length, so those are all equilateral triangles because they make 2 squares. So then I can infer from that 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 hexagon is made up of, you could make up a hexagon of 6 equilateral triangles, right up, snugly up next to each other. Okay, so if you divided that hexagon up into 6 equilateral triangles, you would have 2 sides going across the middle. So one of those sides of those triangles would be 300 millimeters. I know that there are 12 sides on that shape in total, so 300 times 12 would be 3,600 millimeters. But it asks me to give my answer in meters, so I need to think about how many millimeters are in a meter. Milli means 1,000th, so I'll need to divide my answer by 1,000. So 3,600 millimeters is equivalent to 3.6 meters. Here's another one. So a typical question. Notice it is simply just a cube and a cuboid. It doesn't kind of branch out into other polyhedra. This is probably as tricky as it will go. So it says that cube A and cube B have the same volume. How could you work out the missing volume for cube B? So clearly we need to think about the properties of cube A and how we could work out the volume from that. So the volume of the shape is the length times the breadth times the width. So if we know that cuboid, all its edges of 6 centimeters, then we could say the volume is 6 centimeters times 6 centimeters, which would bring us to a total of 116 centimeters as a total volume for that cube. So therefore, if we want to find our cuboid, we know that 6 centimeters times 4 centimeters times that question mark should also equal 209 centimeters cubed, as it says in the question. They have the same volume. So I did 6 times 4, which is 24. 24 times something is 216, or use the inverse, 260 centimeters cubed divided by 24, which would be 9 centimeters. Okay, as the missing length. Another one, referring to, now this is in relation to area. So the area of a rugby pitch is 680 square meters. Don't let that throw you. Meters squared or meters with a little squared is all the same thing. So exposing your children to questions like this, where the vocabulary is slightly changed, and reassuring them that it's the same thing is really good practice, because area can be referred to in slightly different ways. A football pitch measures 112 meters long and 82 meters wide. So they're obviously going to have to apply their knowledge there to work that football pitch out. How much larger is the area of the football pitch than the area of the rugby pitch? Have a go now and see if you can work it out. Okay, now that you've paused it, this is how I might tackle it. So, and encourage them to maybe as a strategy. So I would do 112 times 82 meters. Bring me to, because those are the length and the width of the football pitch, would bring me to a total area of 984 meters squared meters. And then I would the difference from those. I've got my 9,184, subtract 6,108, which would leave me with 3,076 squared meters. Okay, so it's 376 squared meters larger. Okay, so that brings us to the end. I hope you found it useful, and I hope you have got ideas now about misconceptions and roughly what the progression is from Key Stage 1 to Key Stage 2. So here I've got some useful resources. When you're teaching 3D shapes and you're looking at maybe giving some children a challenge or an extension question where they have to kind of apply their knowledge of bases and vertices, there's a really formula that Euler came up with that they can use to investigate with 3D shapes. So here's the website for you to refer to kind of set that up as a task with your children if you find that some are finding it quite easy to identify bases, edges and vertices, and you want to kind of extend them with a nice navigation. Properties of 3D shapes. So earlier on I mentioned a website that had lots of access to the properties. Let me just, maybe I can show you here. So I'll just show you at the top. This is it. So it kind of breaks down the shapes. You can go to shape, show you a bit of a vision there, and so you can see a video of it sort of moving around, draw spaces, lots of information about them. So examples, lots and lots of different kind of ideas about how you can kind of understand those. So very useful website looking at the properties of 3D shapes, and this is a geometry in prisms. And you can kind of go through lots of different areas here, just something to kind of explore. Sphere. Okay, so there. And then also, last but not least, I mentioned a NCTEM glossary, which is and it is literally my Bible. I have it on my desk. From Key Stage 1 to Key Stage 3, and I love it. It's got a content, not just geometry, it's just everything you need to know in maths. But for someone, if you're a bit like me and you need a visual or a picture example, it's really, really helpful, because it will kind of give you a definition. It will outline which key stage you need to kind of be familiar with that vocabulary, and it gives you examples, which is really, really helpful, I find personally, and lots of my staff in my school use it as well and found it really useful to refer. So there you have it. That's definitely something I would recommend just printing off and having a copy to kind of refer to. So yeah, so that's this link at the bottom here. Okay, so bit of time for reflection until the next SOS session. What have you learned today that you might trial with your children in the classroom? Can you think of 3 things? And just have them in your mind and see if you can, and see how you get on with them this week. And let me know how you get on, or if you have any questions. My email address is andrews@sfet.org.uk. Okay, thank you very much for listening to my session on geometry. Bye.